I'm going to give a little background to something that we had talked about yesterday. We had talked about local linearity, and we had talked about linear approximation and using the equation of a tangent line to approximate values of a function. And here's something else that we can talk about. So you might have some function, y is equal to f of x, and we might wonder, what's the change in the function value when x goes from x1 to x2? And this can become very inconvenient if your function is inconvenient. If your function is something like ln x, this is not something you can do in your head. But we do know that if you look at the function that I've drawn here, the change in y, well, that's just a change in a vertical distance. So the height of y sub 2 minus the height of y sub 1. And that's going to correspond to some sort of horizontal distance. So we have change in y over change in x. And one thing we do know, we did talk about the fact that we have this definition. If we take the change in y over change in x, if we take, in fact, the slope of the secant line and look for the limit as the change in x approaches 0, that's going to be equal to the derivative. And that's something we've spoken about a lot. It's just the definition of the derivative. Had we left off the word limit, though, we would only have an approximation. So we could say delta y over delta x for just small values. That will approximately be equal to the derivative. So in fact, we could say delta y is going to be approximately equal to f prime of x times delta x, which is, in fact, we could talk about delta y as y minus y sub 1 and delta x, x minus x sub 1. So this ends up looking a lot like the point slope equation that we were using yesterday. Okay, what is true is that dy dx is equal to f prime of x. And as soon as we talk about dy dx, that is the derivative. So this is really almost redundant. But if I was going to talk about this, I'm not really referring to the function at all. I'm really referring to, in fact, if our point of tangency was at x sub 1, the only thing I'm really talking about is the points on this line. So if I then said dy is equal to f prime of x times dx, this is my change in y along the tangent line. And dx is my change in x along the tangent line. So when I talk about dy here, I would say as x goes from x sub 1 to x sub 2 along the tangent line, notice my climb in y along the tangent line in this situation happens to be bigger. So this ends up being my dy. This distance, this smaller distance, in fact, is my delta y. So here is the distinction we're going to make. Delta y, really, truly, we can use this as an approximation, but delta y is just the change in y values. This truly is the change in values of the function. Dy is the change in values along the tangent line. What we can say, though, is that, let's go back to our limit. If delta x gets closer and closer to 0, they are a really good approximation. So if we want to approximate the change in y, if we want to use the change in y is approximately equal to f prime of x times delta x, we can use that. We can substitute in this equally good equation, dy is equal to f prime of x times dx. Notice delta x and dx are the same amount. Again, dy is the change in y along the tangent line. Delta y is the change in y along the function. But for very, very, very small values of x, we can assume that they're virtually the same. This, in fact, is called a differential. A differential is a small change in y. So we use a differential to approximate delta y.